Hey, Joe, what's the outlet pressure to the superheater?
Let's see. It's running at 850 pounds.
Hey, thanks.
All right.
Quite a night last night.
Well, you guys go bowling?
Oh, yeah, did pretty well. Hey, I hear the boys in the operating room had quite a control upset last night with boiler number 2.
Oh, yeah. Pressure got so high it lifted the safety valves. Yeah, I could hear them clear over at the instrument shop.
Just what do we mean when we use the term pressure? Imagine a tank which contains a pressurized fluid. This air receiver, for example. A compressor pumps air into this tank for use in operating instruments, controls, and other pneumatic devices. Let's say the air pressure inside the receiver is 100 pounds per square inch. What does that mean? Pressure is defined as the amount of force applied by a pressurized fluid on each unit area of its container. The compressed air in the tank exerts an equal force in all directions. If the pressure in the tank is 100 pounds per square inch, that means the air is exerting a force of 100 pounds on each square inch of the tank's surface. Another way to understand the relationship between pressure and force is to look at the force, and therefore pressure, exerted by a quantity of liquid on the bottom of its container. Imagine that this container is a 12-inch cube completely filled with water, so we have exactly 1 cubic foot of water. The bottom of the container has an area of 12 times 12, or 144 square inches, and we know that 1 cubic foot of water weighs 62.4 pounds. The total force applied to the bottom of the container is 62.4 pounds. We said pressure is force per unit area. How much pressure is applied by the column of water over each square inch of the container's bottom? We can determine the pressure applied to 1 square inch by dividing the total weight, or force of the water, 62.4 pounds, by the surface area, 144 square inches. Therefore, the pressure applied to each square inch of the container bottom is 0.433 pounds. This pressure caused by a standing column of liquid is called hydrostatic head. Hydrostatic head varies with the height of a liquid. It also varies with the liquid's mass, or density. We'll learn more about density in a few minutes. So, pressure is equal to force divided by area. We can see from the pressure formula that changes in either force or area will cause pressure to change. For example, if area increases, pressure decreases, and if force increases, pressure increases. By substituting the most common units for force and area in the pressure formula, we can determine the most common unit of pressure. If pressure is equal to force in pounds divided by area in square inches, then the unit of pressure will be pounds per square inch. This is usually abbreviated PSI. As you know, the Earth's atmosphere exerts a pressure on the face of the Earth and everything on it. This pressure is referred to as atmospheric pressure. Although it varies with weather conditions and altitude, atmospheric pressure is usually about 14.7 psi. Atmospheric pressure must be considered and allowed for in instrumentation and control systems, which measure pressure in plant systems. Most industrial pressure gauges and instruments indicate what's called gauge pressure. Gauge pressure is actually the difference between atmospheric pressure and the system pressure that's being measured. Gauge pressure is usually expressed in pounds per square inch gauge, or PSIG. Some pressure instruments, however, measure and indicate absolute pressure. Absolute pressure is measured without regard to atmospheric pressure. That means that the complete absence of any pressure, or a perfect vacuum, would result in a reading of 0 on an absolute pressure instrument. A common unit of absolute pressure is pounds per square inch absolute, or PSIA. Here we see 2 pressure gauges connected to the same process system. Do you think both gauges are reading accurately? If you said yes, you're correct. If both gauges are indicating the same pressure, the difference in readings between a pressure gauge indicating gauge pressure and one indicating absolute pressure should be equal to the atmospheric pressure, about 14.7 psi. Another way to measure pressure is to relate it to the hydrostatic head of a column of liquid. That's the principle at work in a manometer, such as this one. This manometer is a U-shaped tube containing a liquid. A graduated scale is used to indicate the height of the liquid in the tube. In this example, for demonstration purposes, the liquid used in the manometer is colored water. This well-type manometer has a single tube. As the pressure on the liquid changes, it causes the liquid level to change until the hydrostatic head of the liquid in the manometer equals the pressure being applied. The pressure value is read in inches of liquid. A change in pressure of 1 psi is equal to a change of 27.7 inches of water. Manometers like this one are sometimes found in industrial applications. In most cases, however, gauges or other pressure instruments are used, but they can be calibrated so that inches of liquid indicates the scale value. This gauge, for example, indicates pressure in inches of water. Here, two manometers indicate 100 inches of water, but the liquid heights are different. Remember, we said that hydrostatic head varied with the mass or density of the liquid as well as its height. The reason these two manometers don't have the same level is that they're using two different liquids, water and mercury. Since mercury is heavier than water, it doesn't rise as high as water when the same pressure is being measured. The term used to compare the mass of liquids is density. Density is calculated by using the formula density equals mass divided by volume. Typical units of density include pounds per cubic foot, pounds per cubic inch, and ounces per cubic inch. Another term that you're probably familiar with is specific gravity. One use for specific gravity is checking a battery's state of charge. The specific gravity of a battery's electrolyte is frequently measured as an indication of the battery's charge. Specific gravity is a ratio that compares a fluid's density to the density of water. The formula for specific gravity is specific gravity equals the density of the fluid being considered divided by the density of water. For these purposes, the standard density of water is 62.4 pounds per cubic foot. In working with the instrumentation and control systems in your plant, you may sometimes need to convert between different pressure units. You may also need to determine and compare the densities of different fluids. Your workbook contains a number of useful formulas for these calculations, as well as conversion tables.
What's the level in the number 6 makeup tank?
How long will it take to fill a storage tank if we maintain this flow?
How many gallons do we have in the batch tank?
If we keep going at this rate, will we empty the feed tank before the end of the shift?
To find the answer to any of these questions, we would have to know the volume or level of the liquid in a container. As we're about to see, volume and level are directly related quantities, but they are not exactly the same thing.
Paul, how's it going?
Hey, Mike, how you doing?
I'm doing pretty good. Look, I got a question for you.
Yeah.
Now, the level in the number 6 feeder tank is 13.5 feet. Now, if I wanted to know how many gallons were in the tank, how would I calculate it?
You'd have to calculate the volume in the tank by taking the formula for the volume of a cylinder and substituting the diameter of the feed tank and the height of the fluid. Then you'd solve the formula and convert the answer to gallons. It's pretty easy to do. Here, let me show you. The formula for volume is...
The term volume refers to the amount of space occupied by an object or fluid, in this case, the space occupied by the fluid in a tank. Volume can also be used to express the capacity of a container. For example, if we know this tank's capacity, and we know that it's half full, we can calculate the amount of liquid it contains. First, we have to know its total volume or capacity. The volume of a container can be calculated from its dimensions. If this rectangular container is 2 feet wide, 2 feet high, and 3 feet long, we can find its volume by multiplying these values together. The formula for the volume of a rectangular container is length times width times height. In this example, 3 times 2 times 2 is 12. So the total volume or capacity of this tank is 12 cubic feet. If the tank is half full, it contains 1/2 of 12 or 6 cubic feet of liquid. Now, how does volume compare with level? Level is defined as the location of the interface between two phases of a substance. For example, the interface between the steam and water in this boiler steam drum. Or the location of the interface between two substances, such as the liquid and air in this tank. The level in a tank or vessel can be measured with a simple device, such as this sight glass. A sight glass is a transparent tube. The bottom of the tube is connected to a point on the tank which is below the liquid level, while the top of the tube is connected above the liquid level. So, if the tank is vented to atmosphere like this one, the top of the tube is also vented to atmosphere. In this case, two overlapping sight glasses are installed on a tank. Since liquids seek their own level, the level in the sight glass tubes will be the same as the level inside the tank and can be directly observed. Sight glasses are accurate, simple, and reliable devices, but they also have limitations. They provide only a local indication of level, and they can present a hazard if broken. Instrumentation systems that measure and indicate level are frequently provided in addition to or instead of sight glasses. They enable accurate remote level indication and control. There are many ways that instrumentation systems can measure the level in a tank or vessel. One method makes use of a principle we discussed in the segment on pressure, that the hydrostatic head of a column of liquid, in this case the level in a tank, is proportional to its height. You'll recall from our earlier discussions that there is a direct relationship between the height of a fluid and the pressure it exerts on the bottom of its container. This tank is partially filled with fluid. A transmitter senses pressure at the bottom of the tank and produces a signal proportional to the pressure. The instrumentation system then compensates for the density of the fluid and generates a signal proportional to the tank level. Such a system would not be accurate on a closed tank which is pressurized. Now, the pressure at the bottom of the tank is a combination of the hydrostatic head of the liquid in the tank and the vapor or gas pressure on top of the liquid. Pressure on the bottom of the tank does not correctly indicate the level in the tank. In this case, a differential pressure transmitter senses pressure below the liquid level and above the liquid level. The pressure measured at the top of the tank cancels the vapor or gas pressure portion of the pressure measured at the bottom of the tank. The difference between the two measured pressures, or differential pressure, is the hydrostatic head, which is proportional to level. When pressurized vessels contain steam or some other vapor which could condense in the upper low-pressure reference leg, the level indication would again be extremely inaccurate. We would now be sensing the hydrostatic head of the condensed vapor as well as the static vapor pressure on the reference leg. When condensation could be a problem, the upper sensing line is intentionally filled with liquid. Now, the differential pressure determined by the instruments is the difference between the hydrostatic head of the filled column, the reference leg, and the hydrostatic head of the liquid in the vessel. After compensation for the known height of the reference leg and the densities of both fluids, this differential pressure signal is again indicative of only the hydrostatic head or level of the liquid in the vessel. No matter how it's measured, level is a volumetric measurement. It can be used to directly determine the volume of fluid in a container. In fact, many level indicators are calibrated in units of volume. If we needed to know the mass of fluid in a container, we would have to multiply the fluid's volume by its density, or an instrumentation system could measure the fluid's weight. We have seen only two of the many ways that level can be measured. As you continue your study of instrumentation and control systems, and as you become familiar with the systems in your plant, you'll learn about other level measurement methods. Your workbook contains some additional information on level measurement, some formulas for calculating the volume of different shaped containers, and review questions to allow you to check your understanding of these topics. As you know, the molecules of all substances, even solids, are constantly in motion. Temperature can be defined as the measure of the internal molecular activity of a substance. When heat is added to a substance, molecular activity increases. This is seen as an increase in the temperature of the substance. Temperature can be measured and indicated on several different scales. In most instrumentation and control systems, you'll find that temperature is displayed on the Fahrenheit or the Celsius scale. There are several methods of measuring temperature. The method for a particular system is determined by the range of temperature that needs to be measured, and by the range of the temperature sensor. The sensor chosen must also be compatible with the other components of the instrumentation system. Industrial bimetallic thermometers are mechanical devices. Most work on the principle that when their temperature is changed, different metals expand or contract at different rates. Here we see a thermometer sensing element made of two dissimilar metals bonded together. When the element is heated, the two metals expand. But if one of the metals, the lower one here, expands more than the other, this causes the element to bend. In an industrial thermometer,